This question is about the aircraft climbing performance. So let's first go through the question itself. And we have the features of this aircraft, for example, the mass, wing plan area, the drag polar. The drag polar is very important, and it has two components. The first is the parasitic drag, the other is the induced drag, which is related with lift generation. So that's why we have CL in. We also have the engine thrust, the true airspeed, and ambient pressure and temperature. So also we have the assumptions. First assumption is thrust remains constant for the range of speed and altitude. And the third is we can assume small climb angle. Okay, so the first question is to calculate the climb angle. So we know the climb angle is defined by arc sine T minus D divided by W. The right hand side is excess thrust. So according to the question itself, we know the thrust, it's 260 kilonewton, and we know the mass, so we need to calculate the weight, and just m times g. Okay, so now we know T and W, and in order to calculate the climb angle, we need to know the drag D. And in order to calculate the drag D, we need to go back to the drag polar. So as I introduced earlier, the drag polar consists two parts. The first is the parasitic drag CDP, and the later part is the induced drag. And because it's related with lift generation, so we have CL in. Now, to get CD, we need to know CL, right? And in order to get CL, we can move our eyes towards the right corner, top right corner. We see the aircraft climbing, and we can see the weight component along the direction perpendicular to the flight path. That's W times cosine theta. Theta is the climb angle, and that should be equal to L. So first of all, we have CL, lift coefficient definition, and we have L and a rho unknown, and also L equals W times cosine theta. That's from the component perpendicular to the flight path. Okay, and so this is part we need to apply the assumption. Because we assume the angle is small, climb angle is small, so theta is small, then cosine theta can be approximated by 1, that's L, can be approximated by W. And then for CL, we have the L replaced by W, right? And the other question is to get the density rho. And so we know the pressure and the temperature of the aircraft where it's climbing. So in order to get rho, we need to do the interpolation based on the ISA table, International Standard Atmosphere. So I've listed part of the table in here, and that's at height 750 meter and 1000 meter. We can see the temperature is between these two heights. So if we do the linear interpolation, we can find the density, which is 1.1176 kilogram per meter cube. So we know the L and we know the density, and also because velocity is shown in knot, so we need to convert it into meter per second. That's 162.036 meter per second. And then we can calculate CL, lift coefficient is 0.41. So we know the lift coefficient, we just trace back the drag polar, and we can have CD, which is 0.0247, which is quite small. Okay, then we can have the drag based on the definition of CD, half rho v square times S times CD. And so the drag is 103.82 kilonewton. Now we can go back to the initial definition of gamma by replacing T, D, and W. And we can find the climb angle is 5.199 degree, and it's a small angle. It confirms the assumption we made also. The second question is to calculate the climb gradient, and we know the climb gradient is measured in percentage, and it's exactly the excessive thrust. Okay, so because we've calculated D, T, and W, so we know the climb gradient is about 9%. Now let's move to the third question. Calculate the rate of climb. Basically, it's the vertical speed, and it follows this relation, and it's quite straightforward. And we just plug in the numbers. The vertical speed or rate of climb is 14.668 meter per second. Okay, so the fourth question is to calculate the best rate of climb Vx, and also we know Vx is equal to the minimum drag speed for straight and level flight, and also we assumed the climb angle is small, so we can treat the climbing procedure as straight and a level flight. And now we need to go back to the drag polar, and when the minimum drag speed is achieved, what happens is the parasitic drag equals the induced drag. So that's a hidden information. And then we need to just equal the two components. We can have the lift coefficient for minimum drag, which is 0.51. And this is what these two relations we've get them already from previous questions. And so first is the definition of lift, and the second is we assume lift equals the weight because of the small climb angle assumption. And finally, we can get the Vx is 145.22 meter per second. So that's a best rate of climb. And the fifth question is the minimum drag. And so we have the drag polar, we have the CL minimum, and then we can have the CD minimum just using the drag polar, which is 0.03. And then we just calculate the drag based on the definition of CD. So we have half rho v square times S times CD minimum. And remember, because the minimum drag is happens when the aircraft is flying at Vx, and eventually we have the minimum drag calculated. The last question is a calculation of maximum climb angle, and we know the climb angle, sine climb angle gamma equals excessive thrust, and the maximum climb angle means the gamma is the largest. In that case, we need to apply d minimum into this relation. So finally, just getting those numbers, we have the maximum climb angle is 5.29 degree.